Hello, I'm going to be doing an explanation of problem 4 on test 3. It involves a conducting wire being pulled at a constant speed by a force of some arbitrary magnitude through an electromagnetic field. And yeah, let's just go ahead and dive right into it. So the first thing you need to do is determine where the charge is going to be building up as a result of the wire moving, or the conducting loop moving. Since the velocity of the moving charge of the charges is in this way, and the magnitude of the electric field is going into the page, of the magnetic field is going into the page, and we know that in a conducting loop the movable charges are negative, we use the right hand rule to determine that the negative charges will collect at the bottom, and that's matched by a corresponding positive charge at the top. And there's a gradient of charge buildup due to the entirety of the loop not being inside this magnetic field. There's this open region right here where there's going to be no charge buildup whatsoever, so it's going to be relatively neutral, and that's going to cause that gradient. And that's going to cause a current moving in the clockwise direction. So let's go ahead and draw that now. And I know this because the large electric field that's acting right here acts almost as a battery, and it provides a potential difference across the entirety of the loop. And I know that the electric potential is positive here, so for that to be possible, the electric field, or the current, has to run in the direction opposite the magnetic field. I mean the electric field, and the electric field goes downward. Alright, now let's go ahead and draw the force magnitude vector that's represented by it represents the net magnetic force acting on the conducting loop, and that will be in the leftward direction. And I know this because this is due to the force acting on the wire, and we know by the right hand rule that since the current is going upwards towards the top of the page, and the external magnetic field is going into the page, the corresponding force on the wire itself is going to be to the left. And we know that since it's moving at a constant speed, these two forces must be equal. So let's go ahead and write that down. F magnitude, the magnitude of the magnetic force acting on the wire is equal to the force applied. And that'll help us segues nicely into the next part of the problem, where we have to solve for the current of the wire. So the current of the wire is dictated by the magnetic force is equal to IHB. And we know that from the length of the wire equation, the forces balance on these ends and cancel out, so the only length of the loop that we really need to worry about is right here. This is outside of the acting external magnetic field, and we know that F mag is equal to the magnitude of the force applied, so we go ahead and substitute that in. And then we use algebra to solve for I, and we're given that I is equal to the magnitude of the force applied divided by the height of the wire H and the external magnetic field applied. Now let's move on to the second part of the problem, where we have to determine the speed of the loop. And we know that the overall voltage in the loop is equal to 0, or the voltage in the loop if you were to travel around the loop, and that's given by EMF minus IR, because the loop has an internal resistance of R, and I is the current, and IR is equal to volts, and the EMF is equal to the voltage supplied by this region right here, and that is equal to the magnetic of the electric field caused by this charge distribution times H. So let's go ahead and plug that in. Oh, almost forgot, equal to 0. So EMF is equal to IR, which is equal to EH. And we already know from the first part of the problem that I is equal to the mag F over HB. So let's go ahead and plug that in here. Times R. All right, go ahead and solve for the electric field. All right, now that we've got all that done, we notice that for this to be in a steady state, the magnitude of the force attributed to the electric field here has to be equal to the magnitude of the force attributed to the moving of the charges in this rightward direction. So I'm going to go ahead and write that out. So F. All right, I'm just going to write it out completely. So we know that the force acting on a charge is VBH, and we know that since this is a steady state, the force done by the electric field here is equal to the force done by the magnetic field, the external magnetic field. So I'll go ahead and write that. So EQ, or all right, I went ahead and simplified by already canceling out the Q's that would be on both sides of this equation. And now we can go ahead and solve for V, which is the velocity, and we're given E over VH, and as we solved in the first part of the problem, E is equal to F times R over H squared B. So let's go ahead and plug that in. H B squared is H cubed. Hold on. A little confused in my mathematics. It's not VBH, it's just VB. It's the force is equal to QVB. My apologies. I don't know why I included that extra H. I thought things were looking a little wonky. So the velocity is just equal to E over B, which is equal to the magnitude of the force applied times the resistance of the loop over H squared times B squared. And that's the entirety of the problem.